Hello everyone, it's Mohammed Rafid and today I'll talk about triple point and critical point. So we have the phase diagram foundation. Phase diagram is a graphical representation of substance state under varying temperature and pressure. We have two key points, which is triple point and critical point, mark a unique phase equilibrium conditions. And we have three phases: solid, liquid, and gas, regions separated by equilibrium curves. And we have equilibrium lines, sublimation, fusion, and vaporization curves. Triple point definition: the unique combination of temperature and pressure, where all the three phases, solid, liquid, and gas, coexist in thermodynamic equilibrium. So we have all the three phases, solid, liquid, and gas, at the same point, which is in 273.16 Kelvin. That is the temperature, and the pressure is 611.657 Pascal. We have it says triple point is unique for each substance and serves the international standard of for temperature calibration. The critical point definition: the highest temperature and pressure at which a substance can exist as a distinct liquid and gas phase in equilibrium. Beyond this point, the distinction between liquid and gas vanishes. So the critical point of water is the critical temperature is 647.096 Kelvin, and the critical pressure is 22.064 megapascal. Beyond the critical point, the substance enters the supercritical fluid region. We'll see it later. Now we have triple versus critical point. Triple point, all the three phases coexist. Minimum liquid pressure, unique fixed values, reference for temperature. We will see later what this means. Critical point, liquid gas boundary ends, maximum coexistence pressure, supercritical region begins. So we have, this is the phase diagram I talked about before. So this is the pressure and temperature, and this is the pressure, the temperature, and we have the triple point. See, this curve is between ice and steam. This curve, this one, is between ice and water. This curve is the water steam curve. The triple point is at this point, water, or let me, is it good? Under the triple point pressure, the water cannot exist. So when we have ice or solid region, when we give it a little bit of heat, it will go to the steam state without going through the water region, because water cannot exist under this pressure. After it, no, we can go from ice to water to steam. See, the critical point is at the end of the water steam curve. So it has the highest pressure, and this one has the lowest pressure at the water region. And after this point, the substance go to the supercritical region. Then you cannot see the water from gas. the boundaries vanishes. See, this is the triple point for water. Now water is boiling now, and freezing, and so all the three phases are at the same time. Water is gas, liquid, and solid, and ice. At this temperature and this pressure. Now we have the critical point. We have substance. Sorry. We will add heat and pressure to it till we enter the critical point, pressure and temperature. So now we are adding heat and raising the pressure. See, the substance are the boundaries between water and gas are starting to vanish. So now we can see the difference between water and steam or gas. Liquid and gas, we can't see it. Became the same thing. This is the supercritical fluid. Now, below the triple point, liquid phase cannot exist at any temperature. Solid directly converts to vapor. Example, dry ice at atmospheric pressure sublimates without melting, meaning the ice go directly to steam without going through water region. Above the triple point pressure, normal melting and boiling occur. Liquid phase exists as the intermediate state. Now we have the engineering applications. We use critical point and triple point in refrigerating HVAC. So engineers design systems using critical point properties for efficient heat transfer and phase change cycles. Meteorology. Triple point of water is 273.16 Kelvin, serves as the international temperature scale reference. Supercritical fluids, chemical extraction and material processing using unique properties beyond critical point. Material processing, phase transition, optimization in manufacturing, and metal handling systems. Now we have thermodynamic Gibbs phase rule. F equals C minus P plus 2, where F is the degrees of freedom, C is the number of components, P is the number of phases. At triple point, F equals 1 minus 3 plus 2, which is 0. 0 degrees of freedom. Temperature and pressure are fixed once three phases coexist. Refrigeration cycles and phase transition. Refrigerants must cross the saturation boundary, the two-phase region, for heat transfer efficiency. And refrigerant properties chosen based on critical point to avoid the supercritical region. So if we go back a little bit, see, this is the supercritical region. This one. We stay, when we design refrigerants, we stay at this point and anything under it to avoid this region. And high latent heat near saturation dome provides efficient cooling capacity. Now we'll talk about supercritical fluids. as I said, it's beyond the critical point above it. Unique properties combines liquid-like density with gas like diffusivity and viscosity, and excellent solvent for organic components used in waste treatment and synthesis, cover edification, dry cleaning, and extraction process. In the end, the key takeaway is triple point is a unique equilibrium of all three phases. It's 273.16 Kelvin for water, and the critical point is the maximum T temperature and pressure for liquid gas resistance, which is 647.1 Kelvin for water. Phase behavior. Properties change dramatically near saturation dome and critical point. Engineering design. Essential for refrigeration, thermometry, extraction, and material processing. And thermodynamic laws, Calibration, and corresponding state principle govern phase equilibrium. And that's all I have for today. Thank you for listening.